So this video lesson will continue our look at waves, and in particular we'll be focusing on the wave phenomenon known as resonance. So all hard objects, when you tap them or strike them against the side of something, when they will vibrate at a particular frequency, the same frequency every time. And that's called the natural frequency of the object. And the natural frequency of an object is determined by the shape of the object, its length, and the material from which it's made, but not on how hard you hit it. So for example, a wine glass, I could give a wine glass a hard knock against the side of the table, or I could just give it a gentle flick with my finger, and it will always vibrate at the same frequency. And when it vibrates, it will produce sound waves at the same frequency as well. So this phenomenon is applied when we're talking about tuning forks like the ones on the right there, which are used for tuning musical instruments. So a tuning fork will always vibrate at the same frequency when it's struck. So for example, a 440 Hertz tuning fork will always ring at 440 Hertz. And as it vibrates, it will make the air around it vibrate, and they'll produce sound waves of 440 Hertz as well, which you can then use to tune your instrument. So the frequency of these tuning forks depends on the length of the arms and not on how hard you hit it. So you can see here we have a range of different tuning forks from 256 Hertz all the way up to 512 Hertz. And you can see that the ones with the lower frequencies have the longer arms, and the ones with the higher frequencies have the shorter arms. So it depends on the shape of the object and not how hard you hit it. Now, resonance is this phenomenon where if you put vibrations into an object, like you shake an object at the exact same frequency as its natural frequency that it vibrates at when you tap it, then you'll get this phenomenon called resonance, where these vibrations that you're pumping into the object can make it vibrate at the same frequency, but the amplitude of those vibrations will get bigger and bigger and bigger and bigger. It's like amplifying vibrations. Now, the reason this occurs is because you're pumping extra energy into that object by vibrating it, and you're doing it at the exact frequency it likes to vibrate naturally. So the analogy we always use in physics is like a swing. So when you push a swing, the swing will swing backwards and forwards at the same frequency regardless of how hard you push it. And that has to do with the fact that the swing is like a pendulum. And the frequency of a pendulum depends on how long the pendulum string is, in this case the chain that holds the swing up, and not how hard you push the pendulum. If you push the pendulum harder, it'll travel faster, but it'll also swing further, so the total frequency will be the same. Now, resonance in the swing occurs that if you time the push just right, as the kid on the swing goes past, every time you push on the back of that kid, the frequency will remain the same, but you're pumping extra energy into that system and causing resonance. So the amplitude, in other words, the size of the swing, will get bigger and bigger and bigger. So if you get your timing right, every time you push that kid as they come past on the swing, they're going to go higher and higher up. So that's an analogy. That's basically how resonance works. So we can consider a swing in a playground to be an example of a resonance system. Now, resonance can be both good and bad. You have to be a little bit careful about these things. In some systems, if you allow resonance to occur, then the vibrations can build up to a really dangerous level, and that can potentially cause damage or even destruction to the object that you're making vibrate. So a classic example of that is using sound to break a wine glass. If you play sound at the same frequency as the natural frequency that the wine glass vibrates at, then you can make the vibration in that wine glass get bigger and bigger and bigger, and because the glass that the wine glass is made out of doesn't really bend very much, eventually you'll get to the point where the vibration is too much for the wine glass and it shatters. So I'm going to skip across now to a video from a BBC series that Richard Hammond hosted, looking at engineering applications in their relation to physics, and he's going to look at basically how you can use sound to break a wine glass, because it's very difficult to do in a regular classroom. Okay, so we'll roll the video.
All physical structures have a particular note they like to resonate at, that they will ring at. With the wine glass, that's particularly audible, and if I just ping it, the vibration of the glass vibrates the air, which we hear as sound.
All objects have these notes?
Yes, they have the notes. Some are more audible than others.
So even the troll has its own note, a frequency at which it resonates. Scientists calculate that frequency by counting the number of vibrations per second. The glass vibrates nearly 500 times a second. And this frequency is its fatal flaw.
So that ping
Yeah.
is important because that's a constant note.
Yeah, it's a physical property of the actual object.
How does that help us with breaking it?
What we're going to do is we're going to turn the process by which we hear the note backwards. So instead of the structure vibrating and we hear the note, we can actually put a vibration through the air and that will make the structure vibrate in sympathy. If you produce exactly the right note with the guitar that matches the note of the glass, then the glass will resonate.
That means if you replay the exact same note that the glass produces, you can make it vibrate in sympathy without even touching it. It's called resonance.
Eventually, the glass will vibrate so much that it will shatter.
So it really is as simple as that. This has a note. It's a frequency at which it likes to vibrate. But if we reverse the process, if we send the same vibrations back to it,
Yeah.
it'll just vibrate in sympathy with
Yes.
them
Yes.
until it gets carried away and breaks. So we need to match this to that.
Exactly.
So they're both singing the same note.
Exactly right.
It sounds spookily simple, I don't believe it.
To produce the lethal note for the glass, we tune the guitar to the exact same note the glass itself produced. Slow motion footage shows the glass wobbling like jello until it can take the resonance no longer.
Now, as far as we know, that's never been done with a guitar before. But the principle is exactly the same as the cartoon soprano opera singer and the glass breaking. The point now is, what's the connection between that and Trolley?
Okay, so you can see there that what they did, they flicked the wine glass, they recorded the sound it made, they analysed it to determine which frequency it was ringing at, and then they played the exact same note back on the guitar. Now, it has to be fairly loud for that to work, but it's not the loudness that's causing the glass to break, because we can see that it only happened at one frequency. If it was just the loudness, you could make the wine glass break at any particular frequency, but it has to be just the right one. So that's an example of resonance. Another example of resonance comes when you're looking at designing large structures like bridges or skyscrapers. So it turns out that just like a tuning fork or just like a wine glass, a bridge or a skyscraper has a natural frequency it likes to vibrate at. And if the wind, or if you're talking about something like an oil rig in that previous video, the ocean waves, if they're coming in at the same frequency as the resonant frequency or the natural frequency of your building, then that can cause really large vibrations in your building, and that could potentially cause it to collapse. So these days, engineers are very smart about this, and they design their systems so that they won't collapse because of resonance. But, you know, back a couple of decades ago, people didn't really know much about that. They certainly didn't design their buildings to take account for resonance. And you end up with things like we're going to see in this video here, which is from the 1940s, from a place called Tacoma Narrows, which is a bridge across a narrow sort of gulf of water in Washington State in America. Now, this bridge was built in 1940. It was a really flash bridge for its time, really big. But they didn't design it for resonant effects, so it lasted for about 4 months, and then eventually resonance from the wind that blew through this canyon caused it to collapse. So we'll just have a quick look at this now.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
So there we go. So I think they mentioned there were no human victims of that accident. Luckily, everyone was able to evacuate in time, but unfortunately, there was one dog that died. There was a Cocker Spaniel named Tubby who was stuck in the back of the car and died when the bridge collapsed. So poor Tubby. All right. Now, resonance is not always a bad thing. In fact, there are many things that we rely on resonance to help them to work. So a classic example are many kinds of musical instruments. In particular, the one we like to talk about in physics are acoustic guitars, violins, cellos, those kinds of things. So if you think about what a guitar or a violin is, it's a series of strings of different lengths that vibrate at different frequencies when they're plucked in the case of a guitar, or I don't know what the word is, sawed at with a bow when you're talking about a violin or a cello. And those strings vibrate, and as they vibrate, they produce sound at the same frequency. However, if you just had the strings by themselves, the sound that produced wouldn't be particularly loud. It'd be hard to hear. So what you do is you take your strings on your guitar or your violin, and you attach them to a large wooden box, a large hollow wooden box, I should say, called a resonator underneath. And what happens is when those strings vibrate, the vibrations pass into the inside of that resonator, and they cause the air to resonate at the same frequency, and that basically amplifies the sound that's coming out of the strings and makes it louder so it can be heard. So that's for an acoustic instrument. If you think about an electric guitar, they have the same kind of shape as an acoustic guitar, but they don't have that hollow box. The board on an electric guitar is just a flat board. It's just there to hold the strings in place and all the other attachments to things like jacks, guitar jacks, and all that kind of stuff. So they don't need an amplifying thing because in an electric guitar, the amplification is provided by the amplifier you connect it to. But resonance is very important in musical instruments. And then another example, and we'll talk about this in very basic terms, is when you're talking about tuning a radio or tuning a TV to pick up a particular station or channel. So a radio antenna or a TV antenna is just a series of metal poles of different lengths. Now, the length of those metal poles is designed to pick up a certain range of frequencies, but it does pick up all of the frequencies at once. So like an FM antenna might receive everything from 70 megahertz, that's 70 million hertz, all the way up to 120 million hertz. Now, if you tried to listen to that radio without a tuner in it, you would hear all of that at once. You'd hear all of the static and all of the different radio stations overlapping. You wouldn't be able to hear anything. It'd just be a mess. So what you need is you need a way of picking out just one station from that antenna and getting rid of all of the other stations. So just one frequency. So without going into too much details, because it's quite complicated, but basically your antenna in your radio or your TV is connected to a special electronic circuit that's designed to resonate at one particular frequency. And that works because radio and TV are examples of electromagnetic waves. So just like sound waves can resonate, and just like vibrations in bridges can resonate as well, electromagnetic waves can also show resonance. So what we're trying to do here is get an electronic circuit that resonates at one particular frequency. And what that does is it amplifies that one particular frequency so it's stronger than the rest. So for example, if you were trying to listen to, say, Fresh FM, I don't know what you kids listen to. If you were trying to listen to Fresh FM, you'd adjust your radio circuit so that its resonance was at 92.7 megahertz. So we've amplified that particular frequency, which is the one you want to listen to, and all of the other ones would be sort of rejected. So that filters out just the one frequency, so when your radio's tuned to that particular frequency, you hear that and you don't hear all of the other frequencies at the same time. So that's an example of how resonance can be used for a useful purpose. All right, so that's all I have to say for now. And next video, we'll dive a bit further into waves and we'll look at interference of waves, which is what happens when you have two or more different waves combining at a single point in space. Okay, I'm out for now.